Welcome to this course on the time value of money, one of the most fundamental ideas in all of finance. Over the next few lessons, we'll build the tools you need to compare amounts of money that arrive at different points in time, from a single payment to a whole stream of cash flows. In this first lesson, we start with the building block everything else rests on: the future value and present value of a single cash flow. By the end of this lesson, you'll be able to do three things. First, calculate the future value and the present value of a single cash flow. Second, interpret an interest rate in three different ways, because the same number means different things in different contexts. And third, use a timeline as a practical working tool to keep track of when each cash flow occurs. Let's start with why money even has a time value. Here's the question that motivates everything. Would you rather receive $1,000 today or the same $1,000 in 3 years? Almost everyone says today, and they're right, but it's worth being precise about why. There are 3 reasons. First, investment opportunity. Money in your hands today can be put to work and earn a return. Second, inflation. Over 3 years, rising prices erode what that $1,000 can actually buy. And third, risk. A promise of future money is less certain than cash in hand. Together, these are why $1 today is worth more than $1 tomorrow. That preference for money now has a price, and that price is the interest rate, R. What's easy to miss is that the very same R goes by 3 different names depending on the situation. When you're deciding whether to invest, it's your required rate of return, the minimum you'd accept to part with your money. When you're bringing a future amount back to today, it's the discount rate. And when you choose one option over another, it's the opportunity cost, the return you gave up. As the example shows, an investor who demands 6% to lend $10,000 is using that same 6% as a discount rate and as an opportunity cost. One number, 3 perspectives. So where does that interest rate come from? We can break any nominal rate into building blocks. Start with the real risk-free rate, the pure reward for waiting in a world with no inflation and no risk. Add an inflation premium to compensate for lost purchasing power. Together, those two give you the nominal risk-free rate, like a short-term government bill. Then, for a real-world borrower, add 3 more premiums. A default risk premium for the chance the issuer doesn't pay. A liquidity premium if you might have to sell in a hurry at a bad price. And a maturity premium, because longer-dated bonds swing more in value when rates move. Stack them up, and you have the rate the market demands. Now let's put an interest rate to work. This chart follows a single $1,000 investment growing at 7% a year. Notice the curve isn't a straight line, it bends upward. That's compounding. Each year, you earn interest not just on your original $1,000, but on all the interest you've already accumulated. After 10 years, that $1,000 has grown to about $1,967. This forward movement, from present value to future value, is exactly what we'll formalize next. It helps to contrast 2 ways interest can be calculated. With simple interest, you earn interest only on the original principal. Future value equals present value, times 1 plus R times N, so growth is linear. With compound interest, you earn interest on your interest as well. Future value equals present value, times 1 plus R raised to the power N, and growth is exponential. The example makes the gap concrete. $1,000 at 7% for 3 years grows to $1,210 with simple interest, but $1,225 and 4 cents with compounding. That extra $15 is interest earning interest. In finance, we almost always mean compound interest. Over just a few years, that difference looks small, the two lines barely separate. But compounding is a snowball, and time is what makes it grow. Stretch the horizon out to 30 years at 7%, and the same $1,000 becomes about $7,600 with compounding versus only $3,100 with simple interest. More than double. This is why the compounding formula is worth committing to memory. Here's that formula in full. Future value equals present value times 1 plus r, all raised to the power n. Let's name the parts. PV is the present value, the amount you invest today. R is the interest rate per period. N is the number of compounding periods. And the whole term, 1 plus r to the n, is the future value factor. It tells you how much a single dollar invested today grows to arts. The one rule you must never break. R and n have to refer to the same unit of time. If n is measured in years, r must be an annual rate. If n is in months, r must be monthly. We'll come back to that idea in the next lesson. Let's apply it. You invest $4,000 today at an annual rate of 7%, and you want its value at the end of year 5. Plug in. Present value, 4,000. R, 0.07. N equals 5. Raise 1.07 to the 5th power. That's about 1.4026, our future value factor, and multiply by 4,000. The answer is $5,610.20. Notice how the factor does all the work. Once you have it, it's a single multiplication. Now let's run time in the opposite direction. Suppose you know a future amount and you want its worth today. That's discounting, the mirror image of compounding. This chart shows $1,000 due in 10 years being pulled back to the present at the same rate. Today it's worth only about $508. The red arrow points backward toward time 0 to remind you that discounting moves value from the future to the present. The present value formula is simply the future value formula rearranged. Present value equals future value times 1 plus r, raised to the negative n. FV is the known future amount. N is the number of periods between today and that cash flow. R is the discount rate per period. And 1 plus r to the negative n is the present value factor. The example captures the symmetry beautifully. If $1,225 in 3 years is equivalent to $1,000 invested at 7%, then discounting that same amount at 7% for 3 years brings you right back to $1,000. Here's a classic application. A bond will pay $6,000 in 4 years, and your required rate of return is 9%. What's it worth today? Take the future value of $6,000 and discount it by dividing by 1.09 to the 4th power, about 1.4116. And you get $4,250.37. That's the most you should pay today to earn your 9%. Discounting future cash flows like this is the heart of how we value almost every financial asset. Let's push the same bond a little further. What is it worth not today, but 1 year from now at time 1? The key insight is in the exponent. From that vantage point, there are only 3 years left until the payment, not 4, so we discount over 3 periods instead of 4, and the value rises to $4,633.20. The lesson to carry forward. The formula always uses the number of periods between your chosen reference date and the cash flow, not necessarily from today. Let's tie it together. Future value and present value aren't two separate formulas. They're two sides of the same coin. growing a present value forward and discounting a future value back use factors that are exact reciprocals. 1 plus r to the n times 1 plus r to the negative n equals 1, as long as the rate and the horizon match. Hold on to that symmetry. In the next lesson, we'll see what happens when interest compounds more than once a year, and why that changes the rate you actually earn. Let's bring Lesson 1 together with the ideas that matter most. First, money has time value. $1 in your hand today is worth more than $1 promised later, because you can invest it. It hasn't been eroded by inflation, and it carries less risk. Second, one interest rate plays 3 roles at once. It's your required rate of return, your discount rate, and your opportunity cost. And third, future value and present value are 2 sides of the same coin. You grow money forward with 1 plus r to the n, and bring it back with 1 plus r to the negative n, and those 2 factors are exact reciprocals. 2 habits will keep you out of trouble. Always keep r and n in the same time unit, and always count the periods from your chosen reference date to the cash flow. Nail these fundamentals, and you're ready for the next lesson, where interest starts compounding more than once a year.